Yes,
Yeah, it's full screen now. Yeah, yeah. So our next speaker is Professor Andreas Winter. Professor Andreas Winter is research professor at Catalan Institute of Research and Advanced Studies, the Autonomous University of Barcelona. He is a recipient of Humboldt Research Award by the Alexander Humboldt Foundation. Uh, and especially as I know Andreas Winter, he's a big mathematician and theoretical physicist, currently working at the university, as I told you. The area of his research interest spans many diverse topics in quantum information and foundations. Some of his most notable works in quantum information is distillation of secret key and entanglement from quantum states. And in quantum foundational research, he was one of the author of the seminal paper where information causality has been introduced as a physical principle that rules out stronger non-local correlation than quantum correlations. So over to Professor Winter.
Okay, thank you very much for the nice introduction. Thanks for having me. It's a very intense program for people who participate from abroad. It's a bit tricky, I must admit, with lectures and other commitments to find time to tune in. So at least I could make it for my own talk. It's already an achievement, I must say. Yeah, so unlike these many things that the chair has mentioned from my past work, I want to talk about something relatively recent. It was actually a very fun project done with Farzin Salek, who at the time was a PhD student here in Barcelona, now he's in Munich, and Masahito Hayashi, who is of course well known in this community. And it's about hypothesis testing of where the hypotheses are represented by channels. So I want to start very gently. Let's see if we can, yes, here. So let's just start with a bit of warm-up about binary hypothesis testing, which will be the setting of the talk. And then we're going to gradually fill it with quantum physical content. So the binary hypothesis testing traditionally is presented as a choice between two hypotheses, which traditionally are called null and alternative hypotheses, even though there's kind of this inherent asymmetry between them, but we will also consider settings where they are treated on the same footing. And so the general description that kind of goes back to the early 20th century of this kind of way of looking at the world is that one does a test which consists of obtaining some samples, which usually, the samples usually are probabilistic samples, and then based on this sample, you make a choice. You decide which of the two hypotheses you somehow think more likely. And so, because everything is probabilistic, there are errors, probabilistic errors, and they kind of again traditionally we distinguish two kinds, which is they're kind of denoted in this talk alpha and beta. The probability alpha is the probability that the alternative hypothesis is true, but you don't recognize it. And beta is the opposite error, that the null hypothesis is true, but you don't recognize it. So you falsely reject the null hypothesis. Yeah, so I'm not a statistician myself, but I think the names, they come from this thing that the null hypothesis somehow is your kind of current theory of the world, or the a priori most likely explanation. I don't know, in clinical tests, the most likely thing is the patient is healthy, or rather the patient, we're looking for a disease X, the patient doesn't have this disease. And so you want two things of your test. It should recognize, if the disease is present, it should recognize it with high probability, but also you would, since the majority of patients doesn't have the disease, you definitely want a very low probability of a false positive. And so it's very important to distinguish these two probabilities. And usually there's a trade-off, obviously, because in the statistical world, the two hypotheses are not perfectly distinguishable, maybe based on the nature of the samples, maybe based on the nature of our test. We cannot make alpha and beta both zero, but we can make maybe one small at the expense of the other. And so the setting we are kind of considering here is a very traditional one of classical statistics, that we draw many independent samples, whatever that means. In statistically, I guess it's clear. In classical statistics, it means that you have some kind of probability space and you draw IID samples from that space. And so when you think about it, you expect, even if n is large, you don't expect that the error is exactly 0, but they will converge to 0. You can make both of them go to 0 exponentially fast. That's kind of a lesson learned from classical probability. And so what you would like to find out is, I don't know if you can see my pointer, but otherwise I'll have to play around with a zoom pointer. What the game is then, well, the trade-off between alpha and beta becomes somewhat the trade-off between these exponents. You would like to make this C1 and C2 as large as possible, but again, the trade-off will mean that you can make one large, but the other one will be small, and vice versa. And so traditionally, there are three regimes that one likes to consider. Two extreme ones. The one is called the Stein setting, where we are just interested in one of the two error probabilities. We really only want to minimize the error probability of second kind, the beta, which means we want to maximize C2, but we are not so much interested how fast alpha goes to 0. Okay, alpha will be going to 0 with some law, but we don't care. So C1 is any number larger than 1. We would like to maximize C2. Then there is the Chernoff setting, which is the symmetric one. We are sort of equally concerned about both of the error probabilities. So we want that they are actually equal. C1 is equal to C2, and we would like to maximize this value. And then there is kind of the interpolation between them. This is usually associated with the name of Hoeffding. You fix the exponential rate of 1, say C1, and you would like to maximize the other one. So that will be a function of R. Then, of course, you get, I mean, the first two, they are just functions of your two hypotheses in some sense, if you're really able to maximize. And the last one is a function that interpolates between the two, because you can recover the Stein by setting R equals 0, and you can get Chernoff if you take the section of this function with the identity function. Okay, so that was like just the overview of the kind of setting we are considering. And so now let's do a bit of quantum. So I would just do a brief review of the hypothesis testing of quantum states, which is a very well developed subject, and I will only show the most superficial things so that we can go ahead and discuss the topic of the talk, which is hypothesis testing of channels. And so the two papers I showed on the title page, these two archive preprints, they then contain results that are then discussed in the third part of the talk. So we will, they are kind of, the main thing of this, the main topic of this talk is somehow the role of adaptiveness, which we will define properly for the discrimination of channels. And we will show in which settings this adaptiveness can actually give a noticeable advantage, and in which cases we can actually prove it doesn't. Yeah, so maybe the main thing is this part in green in the outline, that we show certain quantum channels where the adaptive strategies of discrimination is infinitely superior to non-adaptive discrimination in a certain sense. So let's yeah, so this hypothesis testing, the sort of the general setup that goes back to, well, I don't know, names are Wald, Fisher, these kind of people in the beginning of early 20th century. We fill this now with a quantum mechanical interpretation. So that's already peculiar, because we I mean, the hypothesis testing is that basically, well, each hypothesis is represented by a possible quantum state of a quantum system, so that this by itself doesn't give you a sample. So you first have to choose a measurement, and then you have the sample, and based on that you can make a decision. When you the asymptotics n going to infinity, we interpret in this way that we have actually n copies of the state, so which means we have rho tensor n, that's one hypothesis, or sigma tensor n, that's the other hypothesis. And so but I mean, however you describe your test, I mean, this might be some measurement followed by some calculations followed by a decision rule. Ultimately, the laws of quantum mechanics, I can describe all of this by a binary P of M. M and 1 minus M, so M is a positive operator and 1 minus M is a positive operator. That kind of is the integral of all of these quantum operations we do until the final binary choice. So where M corresponds to choosing the first hypothesis, the rho, and 1 minus M corresponds to the second hypothesis, sigma, which is alternative and null, right? And so yeah, so I just used the one rule to write the error probability of first and second kind, and well, then they're just functions of linear functions of M, and because M is subject to semi-definite constraints, and it's between 0 and 1 as a matrix, that means for fixed n, well, for fixed states and for fixed n, if you are interested in, for example, optimizing beta as a function of alpha, that's an STP. So in some sense, that can be solved, and this fact that this is a semi-definite program that's useful because you can write a dual, and sometimes in some certain situations that's also useful to find the solution. But in practice, it's not such a great thing because remember, I mean, I'm interested in this kind of statistician's limit of having many samples, and so I know that I can make alpha and beta go to 0. I'm really interested in how fast it can go. So the exponent, that's a nonlinear thing, and so the exponent, that would be the log of beta divided by n, right? So I take minus 1 over n log of the minimal error probability such that alpha is less than epsilon. That is the Stein setting. I'm not interested in how fast alpha goes to 0, just should be small, reasonably. That's this epsilon. And so we know through the classical works of Yai Petz and then subsequently Ogawa and Nagaoka that for every epsilon between 0 and 1, this limit exists and it's equal to a beautiful quantity, namely the quantum relative entropy, which incidentally had been defined decades before. I mean, the mathematical literature, it's associated with the name of Umegaki from the 50s on purely formal grounds. He writes down this formula, trace rho log rho minus log sigma, which is finite, which is well defined as long as the support of rho is contained in the support of sigma. And we simply declare this number to be infinite when the support is not contained. So that means that the kernel of sigma is not contained in the kernel of rho. So then this kind of thing has a singularity. And in fact, then the theorem is still true. This limit exists and is plus infinity. So this is classical stuff. This goes back to the 90s and early 2000s. A little bit later by Audenat et al., Nussbaum and Scholar, the so-called Chernoff setting. So that means it's a setting when we want both of the exponents to be equal. So this can be coded by trying to minimize the sum of the two error probabilities, taking the log and divide by n, so that it gives us the exponent. So again, this has this limit. We know what it is. It's almost a closed expression. There's a one parameter minimization, and it's this one. So it's this trace of rho to the s sigma to the 1 minus s that has to be minimized over the unit interval. And the negative log of that, that's this exponent. That's this, so I call this, the previous one Stein, I call it S, and the Chernoff I call C. And then by putting these two proofs together, Hayashi and Nagaoka were able to do the general trade-off setting. So this is this function B of R. That's the best exponent of the error probability of second kind, given that the error probability of first kind has exponent R. And so this is given by another simple maximization, where here there is the Petz version of the Petz quantum relative entropy. So it's this kind of thing. ds of rho sigma is, well, there's a normalization here, log trace of rho to the s sigma to the 1 minus s. So it's the same thing that appears in the Chernoff bound. But now instead of just minimizing it, we do a kind of a transform of this. There's a kind of a linear term here in R, and then we maximize over S. So this, for R equals 0, this specializes to Chernoff. No, sorry, to Stein. And when if we want to solve the equation P of R equal to R, we get also the Chernoff bound. Yeah. This is just review. I mean, the latest paper here is already from more than 15 years ago. So since then, people have worked a lot on the so-called second order behavior, for example, what happens if you are, I mean, sort of we have this exponential behavior, so e to the minus constant times n. There is a second order rate that goes with square root n also in the exponent and so on. So those things also have been figured out, at least in the Stein setting. I think Chernoff, maybe yes, but I'm not sure now, so I don't want to say too much about it. So that's the frontier. But for states, that's kind of what it is. I mean, like basically we define the optimal hypothesis testing for states, and then having many copies of the state is just apply the same theory to rho tensor and sigma tensor, and then you need a little bit of matrix analysis to calculate the asymptotic limits. So for discriminating channels, we have to think kind of what our tests look like. Yeah? So in the case of states, it was just make a measurement and apply a rule. Our hypothesis in the rest of the talk are quantum channels. And so that means completely positive and trace preserving maps on the same Hilbert spaces. So again, they are, think of this as some kind of a black box. You don't know what's inside, but both of them have the same input and the same output system. There could be like depolarizing channels with different strength of depolarization, or amplitude damping channel with different degree of amplitude damping, or something like this. You want to figure out which of the two it is. I mean, again, we are only discussing binary hypothesis testing here, and obviously there is kind of a whole world of multi-hypothesis testing. You can also ask similar questions for estimation if you want to estimate a parameter encoded into the channel, but I leave that all for other talks and other works. So arguably, binary hypothesis testing is the simplest one, where you can see some interesting effects already. So what is a test? I mean, how can I test a channel? Well, you can argue I have to use it. I have to provide an input. So you have to prepare a test state, then apply the unknown channel. So that's kind of in my drawing. That's this box with a question mark. And that produces me a state here. I didn't write what it is. So it's basically the channel tensored identity on R applied on the test state rho. So notice that I'm already thinking about generality, because when I can prepare a state, I can in particular prepare an entangled state between the input A and the reference system, which I as experimenter control. Yeah, so at the once the channel does its job and R is subjected to the identity, then I have one of two states, namely depending on which channel has acted, and then I can apply my previous machinery that I have to design a binary measurement that chooses between N or M as the answers, or the guesses. And so when I do this, I can write the error probabilities again in the same way as by using the Bond rule. It's just more complicated, because now I have rho is a variable of my optimization. That's part of the test. Choose rho in a good way, and M is a variable. And both of them are semi-definite, and my formulas, they look like bilinear in rho and M, but it turns out you can recast this optimization as a single semi-definite program and sort of yet in another auxiliary variable. I didn't do this here, but because it's not so relevant for us, but it's kind of it's good news, because that leads to the so-called diamond norm of the diamond norm distance between the channels. And so when we have n channel uses, I mean, the very first reaction you could have is exactly the same as for states. While having n channels, it really means I have n tensor n, or if it's the other hypothesis, m tensor m, right? So like I have one of these two channels. I mean, after all, n tensor power something and m tensor power something, they are both just another pair of channels. I mean, each of them is another channel on a bigger system. And so the most general non-adaptive strategy to distinguish the two hypotheses now is to simply treat n uses of the channel as one big channel and provide a single big input in parallel, which again could be entangled with a reference system. So I'm applying n tensor n, tensor identity, or if it's the other hypothesis, M, tensor M, and so on, tensor identity to my input state. I get here some big state, and then I can apply a binary measurement to decide between them. And so, as before, for fixed N, for a fixed number of copies, for a fixed number of uses, if you want, or that's kind of the number of samples, it is a fact that the optimization, the joint optimization of a rho and M is a semi-definite problem. So it's kind of nice. But it turns out we can do something more general that looks at the same time more scary and more elegant, because we can stagger the channel uses. I mean, already here we could do it like this. In this picture, I mean, I can prepare this big state here, and then I can first apply the first channel, then later apply the second channel, then a little bit later apply the third channel, and so on. Right? That's kind of the luxury of having separate boxes. I mean, if you want, think of these as kind of lab elements. There are these boxes, and all you're guaranteed is that all n of them implement the channel n or the channel m. But your task is to find out which one it is. Yeah, so to do something even more general, you could say, well, I mean, I can prepare just a state for the first channel between A1 and R1, apply the channel as this unknown box, I get an output, then I can process this in some way. This can be very trivial. It could be just conserve the output and prepare another input, but it could be something non-trivial. It causally connects B1 and A2 and also prepares an R2, and so that I can apply the second channel and so on, so that adaptively, kind of quantum adaptively, or maybe more accurately, so iteratively, I will alternate between the unknown channel and some known lab procedure. So everything I can control in the lab is rho, and then this T1, T2, all the way to Tn-1, and the final binary measurement. That will, and so I can again just compose the channels and then write use the Born rule to write the probability for the error probability of first and second kind of alpha and beta, and those will be now multilinear functions in rho, T, I's, and M. And it's a fact that one can turn, if you're interested in the optimization of some function of alpha and beta, this optimization can be turned into an SDP for a fixed pair of channels and for fixed n. And so this is the topic of a theory that goes by many, many different names. So maybe the one that is most well known in quantum information circles. I don't know about the present audience here, that's probably mixed enough. Some people call this a quantum comb, or a causal channel, or a memory channel, or a super channel, or an adaptive strategy. And so formally it can be written like this. So this kind of I mean, if you want, this is kind of a tensor contraction. So each channel is a simple tensor with a single input and a single output. So I write a single arrow. And I contract it with some kind of complicated channel, C, that's the comb, which ultimately is just another completely positive and transparent map that has multiple inputs. Each of these B systems, it takes its inputs, and each of these A systems, it produces its outputs. And there's a final output X. This is this one here at the very end of the comb. That is a classical variable, a 0 or a 1 or n or m. So this X is just a two-dimensional system. And so for this to be, for this to correspond to a kind of a quantum circuit of this form, where I explicitly prepare a state, apply maps, and so on, in the works of Kiribella et al. And of many others, it is shown that this is equivalent to this channel C to be signaling only forward in time, where time goes from 1 to 2 to 3 all the way to n. And so that means no signaling backward. So what this does is that if you trace out the last, so these A systems, they're A1 through AN, if you trace out the last one or the last two, this leads to a channel that only depends on the corresponding input systems. And then all the other inputs are simply traced. They are not relevant at all for the functioning of the channel. So this is the kind of channel. That's the action of the channel. If you C is some kind of multi-input, multi-output channel. If you choose to trace over X, then this corresponds to a channel where the last Bn input is irrelevant. If you choose to trace over X and An, then the last Bn and the Bn minus 1 inputs are irrelevant. So this kind of this composition is equal to another channel tensored with a plane trace. These are no signaling conditions, and like I said, this is an if and only CP map. Can be written as a circuit like in this diagram, if and only if it satisfies all of those conditions. And that is kind of how you do this STP, and it allows you in practice to deal with the optimization over the error probabilities. Now, this was all maybe a little bit abstract, so let's see a little bit what this adaptiveness can do for us in a very simple example. Let's see how much I'm doing at the time. So I took this, I mean, actually in our paper, it's a very important example for us in our paper with Vasin and Masahito, from a paper by Harrow, Hasidim, Leung, and Watrous from quite some time ago. So they came up with these following two channels. They map a 2-qubit system to a 1-qubit system. So it's written like this. The input consists of 2 qubits, A and C. This is kind of A is the input and C is somehow a control and B is the output. And here in these drawings and with this text, I'm trying to describe to you what the channel does, rather than writing kind of one big, which is a bit harder to decode. So what the channels do, they both measure C in the computational basis, and then record and use the result to control one of two channels on the A-B part. And so it's kind of a controlled single qubit channel. And what the control does is, and then it throws away the C. So C, the outcome C, is only used internally for the channel. It's not part of the output. The output is just a single qubit B. And so if the control is 0, each of these two channels does, N applies N0 and M applies M0. And those are very brutal. They just throw away the input, the other input on A, and replace it by a single state. So if the control is 0, the channel on mapping A to B is just a state preparation. But crucially, it prepares one of two pure states, but they are non-orthogonal, so they are not perfectly distinguishable. And if the control is 1, the channel implements a measurement on the A qubit. And in the case of N, so in the green channel, it's a measurement in the computational basis. So it measures projection to 0 and 1. And if we get outcome 0, it prepares a 0, and if we get output 1, it prepares a maximum mixed state. So it's kind of to be avoided because that creates a lot of noise. And then the channel M, that's the red one, it measures in the conjugate basis. So this plus state, that's kind of the 0 plus 1, and minus is 0 minus 1. That's kind of the Hadamard basis correspond of the computation basis. And it does similar things. So if the outcome is plus, it prepares a 1 state, so that's orthogonal to 0. And if it finds a minus, it prepares the maximum mixed state. And so, I mean, obviously these guys, Harrow et al., they reverse engineered this channel in such a way that using adaptiveness, they can be distinguished perfectly, actually. And when maybe, I don't know, if I have time to let you think about it, how would you do this? You see, each of these two channels is able to prepare a state, but they are not orthogonal. But then they are also able to do measurements, but they are not aligned measurements. They are mutually unbiased measurements. So how can you use this? Well, you use the two channels, each of them in the two modalities, first preparing a state and then doing a measurement. And so Harrow et al. They showed that by two adaptive uses of the unknown channel, you can discriminate the two alternatives perfectly. to the extent that you can do all these measurements, that the channel behaves as advertised, and that you can do the final measurement, you have zero error probability. And so how does it go? You apply the first channel with a 0, so that is the state preparation. That what it means is that here is either N0 or M0, so that we will prepare one of two pure states, either the 0, the computational basis state 0, or the plus state, depending on which one it is. And then we apply the second channel with a control qubit set to 1 that will execute a measurement. And the measurement is designed so that it's either the computational basis measurement in the first case, or it's the conjugate basis measurement in the second one. And so that can be summarized here, regardless of what this state here is. The measurement is the measurement in the basis phi and phi orthogonal. Yeah, so it's either 0, 1, or it's plus minus, depending on the two hypotheses. And so what we get here as an output is actually a computational basis state. Namely, we get projector onto 0 if the channel applied was both times n, and we get projector onto 1 if the channel applied was both times m. And so, yeah, with two uses, you can distinguish them perfectly. And you can actually show that with one use, you couldn't do that. And in fact, what Harrow et al. Prove in their paper is that even if you have access to n tensor power n, m tensor power n for any number of copies, you will always have some error probability. So these alpha and beta, these are error probabilities of first and second kind. They cannot both be 0. That's what they show. And so this is kind of a qualitative way of looking at the power of adaptiveness. And so basically in the rest of the talk, I want to explore this a bit quantitatively, also in the relation to the number of copies that we have here. And so let's start with, in some sense, the negative results, which are that this beautiful idea of using adaptiveness, of kind of using the output of the channel to prepare the input to the next channel, where this doesn't actually do anything for us. And so these are all results from relatively recently, last few, maybe up to 5 years. It took a while to put everything together. And so let's start with the Stein setting. So this is kind of the most asymmetric setting, where all you want is that the error probability of first kind is small, bounded away from 1 or going to 0 mildly. And you would like to find the maximum exponent by which the second error probability goes to 0. So this is somehow the paranoid regime in which you want a test that reasonably well recognizes the alternative hypothesis. If it happens to be true, the alternative hypothesis should be recognized with some decent probability. But you are really, really afraid of rejecting the null hypothesis without need. Because maybe that's your standard model, you don't want to just refute the standard model because of some stupid experimental error. So that's the Stein setting. Yeah, we do, it's the same thing as before. We are interested in the -1/n of log of beta when alpha is somehow small. And so it turns out this limit exists. I mean, maybe I was a bit optimistic when I wrote this. I think technically, I mean, when I look at the papers, we also need a limit of epsilon going to 0 here, but the conjecture is that you don't need that. For any epsilon, this should also be the same thing. It's a quantity known nowadays as the so-called amortized channel divergence, and it's a very, very scary beast. It's a supremum of a difference of two relative entropies, of Umegaki relative entropies. So you have two test states, one for rho, one for n and one for m. You're applying n to rho and m to sigma, and you're looking at somehow the difference between the relative entropy of the output state minus the relative entropy of the input state. And you take the supremum over all reference systems in all arbitrary states, including mixed states here. So this is I mean, formally well defined, but it's, I think in practice, basically impossible to calculate. I don't think we know anything about this, how to actually calculate this number. But I mean, that's what you get. This is sort of the information theoretical characterization of what you get from adaptive strategies. This was a result by Xin Wang and Mark Wilde from a few years ago. And basically by stealing HI and PETs, if we do the same thing for non-adaptive strategies, if you just treat N and M tensor power N as some big channel with a single input, you get a similar thing in terms of the regular channel divergence, which is simply you have a single input state and you're looking at the relative entropy between the channel applied to rho and the other channel applied to rho. And so it's kind of the same thing as above here when rho is equal to sigma, because then the second term in the relative entropy is 0. So this, however, needs to be regularized. So this is the regular channel divergence, and then we need to take the many copy regularization of this channel divergence. So again, also this one is almost impossible to calculate. I mean, the single shot one, we have a chance because you can argue that you only need to restrict to pure states here, and R has to be the same dimension as A. So in some cases it can be calculated, but the regularization that kind of does it for us. We can calculate this. But we have a third result, which is due to Fang, Fauci, Berta, and Renner, and maybe some other people that I forgot now. They proved in a separate work that actually these two exponents, so the exponent for adaptive discrimination and the exponent for non-adaptive discrimination, are actually equal. I mean, a priori, one is bigger than the other because adaptive strategy include non-adaptive ones as a special case. Turns out they're the same. And so Fang et al. They proved this by looking at those quantities directly. They proved that they discovered some sort of chain rules for these channel relative entropies. Then in a subsequent work, maybe that was only published maybe last year, Berg, Data, and Wilde and some other people, they prove this more directly. They prove it directly for the hypothesis test. They look at the adaptive protocol that discriminate the two channels, and they show how to turn this into a non-adaptive one without losing too much of the error probability in such a way that the exponent remains the same. And so, so there's two different arguments of proving the same thing, namely that adaptivity doesn't actually help, even though it's to be understood with a grain of salt. So the kind of caveat down here is for a concrete optimal, for a concrete n, if you look at the concrete optimal pair alpha beta of an adaptive strategy, this same pair might not be attainable for a non-adaptive strategy. So that this construction of Berg et al. What it does is it makes alpha and beta suffer a bit, but the exponents remain the same. So the asymptotic of minus 1 over n log beta remains the same. And so then inspired by so that means, well, if you want to see the advantage of adaptiveness, you have to go to for example, the symmetric hypothesis testing, to this Chernoff bound, where both error probabilities go to 0 with the same exponent. So there's another no-go result, if you want, which is the special case of classical and classical quantum channels. So those are channels that measure the input in the computational basis and then prepare a state rho x, depending on the output, or sigma x. That's how the hypotheses are distinguished. It's basically a family of states rho x versus another family of states sigma x, and you can choose by picking the channel input which x you want to see. So that's a classical quantum channel. So if that includes the case of a classical channel, informally at least, namely if when all the rho in x and sigma x pairwise commute, then everything is diagonal in some basis, and then we can represent it by a classical channel. So that's a kind of an interesting case because it simplifies the analysis of both of the non-adaptive and the adaptive strategies. For example, for the non-adaptive ones, you can convince yourself rather quickly that the entanglement between, and in fact, any kind of correlation between the inputs in the reference system doesn't help at all. Very quickly, you can reduce any general strategy to simply choosing an input X to each channel. And the adaptive strategies is kind of almost the same, you have to, for each channel, you have to choose you have to put a classical input X, and that means that the adaptiveness boils down to making measurements to have a classical information on which to base the next channel input. And so both of those, they turn the problem into something somehow sufficiently classical so that we can characterize both the non-adaptive and the adaptive optimal exponents, and for everything, Stein, Chernoff, Hoeffding setting. Like, it doesn't really matter. I mean, spoiler, this slide says we can first calculate these numbers, and also it doesn't depend on whether we allow adaptiveness or whether we look at non-adaptive strategies. So for non-adaptive strategies, like I said, it boils down to choosing optimal classical inputs. And so it's not very surprising the kind of results that we get. For example, the Stein exponent, the optimal exponent to distinguish the two channels is, well, you choose the maximum relative entropy over all pairs of input, over all pairs of outputs. And so this X here corresponds to choosing an input state, a basis state X. That means the channel will prepare either rho X or sigma X, and then I apply simply the Pet's quantum Stein's lemma for states. And obviously I would like to maximize this quantity because that gives me best performance. And the same thing for the Chernoff bound. I can prepare either rho X or sigma X. I can apply the Autònoma quantum Chernoff formula for the exponent, and I want to make it maximal. And again, and the same thing for the trade-off between the two different exponents. So R and P of R are the two exponents of the error probably the first and second. So that's kind of very unsurprising. I didn't even attribute it to anyone. It's like, it's an exercise. I mean, you look at the definition of those quantities in the case of CQ channels. Well, that's very good. So slightly less trivial. Hayashi about 15 years ago, and then in the recent paper with Farzin and Masahito Hayashi, we also for CQ channels, for classical quantum channels, we show that also the adaptiveness doesn't yield any asymptotic advantage. So the asymptotic Stein's exponent is equal to the parallel one, it's this one. The asymptotic, the adaptive Chernoff exponent is equal to the parallel one, it's this one. And the adaptive Hoeffding exponent as a function of R is equal to the parallel one for all rates. And so, yeah, I don't want to show the proof because I'm running a bit out of time, but I want to, I mean, intuitively it comes from the fact that the inputs to the channels are classical. And so even your adaptiveness somehow has to, like the available quantumness in the quantum channel output, it has to destroy that in some sense. If you want to use adaptiveness, the measurements make it kind of useless. Something like the Harrow et al. Example doesn't happen. Okay, so finally, for me, that's the highlight of the paper. Finally, some case in some setting in which we do see a difference between adaptive and non-adaptive separation, and unsurprisingly, it comes from this example of Harrow et al. Because it almost showed it already. So that leaves the previous consideration. It leaves the observation we cannot look for a separation in the Stein fully asymmetric hypothesis testing because their adaptive is asymptotically equal to non-adaptive. And also, we need some kind of sufficiently quantum channel because this classical quantum channel and fully classical channels, they also don't admit any kind of adaptive advantage. And so the starting point, I just want to show a few lines of calculation here. The starting point is, oh, let me see. Yeah, I have to look a bit with the battery actually. I'm not running on, maybe I'm running out of battery rather than of time. Let's see. So we started with a simple criterion from of Rouniard-1 and collaborators that guarantees that the error probability cannot be zero for parallel strategies, for non-adaptive strategies. And so their theorem goes like this. If you write N and M, the two channels in Krauss form, so you have this crossover as EI and FJ, and you form all the products EI dagger time FJ. So this a priori kind of a weird object, but it's a set of matrices. If that span, if if those matrices they span a subspace of matrices, if that contains a positive definite matrix, I mean not just positive semi-definite, but strictly positive definite, then alpha plus beta is positive for all n and for all parallel strategies. That's what they showed in the paper 2008-2009. So we want to make this quantitative. We need a lower bound on the error probability, so we can say that the Chernoff exponent is not infinite. And so we do it like this. So I mean, our test looks like this. We prepare a state phi AR, and then we apply the channel. And if it's just one channel, then we generalize it to n channel uses. So we get one of two states. And so again, I just want to say, I didn't mention it before, without loss of generality, we can assume that this test state here is pure because we can always purify it and then later trace out parts that we don't need. So first observation is the sum of these two error probabilities, alpha plus beta. This is actually just 1 minus the trace distance between those two states, rho and sigma. And so by general inequalities known for quantum states, this is lower bounded by 1/2 times the fidelity squared between two states. Yes, I'm running out of battery. It's really very bad. So let's see if I can save a little bit. Oops. No, I didn't want to do it. Sorry. I need to go back to the full screen. Sorry, it was the wrong button. So yeah, should be back on. Okay. So a little lemma. So we want to look at a concrete linear combination of this EI dagger J with coefficients that have like a L1 condition. The sum of squares of this gamma ij is 1. If this P is strictly positive, then we can show that alpha plus beta is lower bounded by essentially the smallest eigenvalue of P to the power 4, which we assume to be positive, right? So this is kind of, and so applying this to n channel uses, we get a lower bound that goes to the minimum eigenvalue to the power 4n. And so ultimately that gives us an upper bound on the Chernoff exponent, on the log of this alpha plus beta divided by n, that is like this here. So it's the largest eigenvalue of P to P inverse, and 4 times the log of that. And so how do you prove this? Well, we have this lower bound in terms of the fidelity, so we just continue lower bounding the fidelity. The fidelity is the trace norm of square root of rho squared sigma. That's lower bound by the trace of square rho times square sigma. That is lower bound by the trace of rho times sigma, because rho and sigma are dominated by their square roots. And then using the formula for rho and sigma, by this kind of applying the two channels, you can bring the Krauss operators into the game. So this is just an algebraic formula expanding the trace here. And then using Cauchy-Schwarz, we can, instead of having a sum of squares, we can make this into a single square of a big sum. And inside here, that's our P. So we get a lower bound in terms of the trace of something times P, and this something is a state. So this is in turn lower bound by the smallest eigenvalue of P. And so if you put all of this together, you get that the alpha plus beta is lower bounded by 1/2 the fidelity square, which is lower bounded by 1/2 minimum eigenvalue of P to the power 4. And so, like I said, we apply this then to n channel uses of n or of m. Then we can use gamma to the tensor power n as a coefficient matrix. We get P to the power n, and it has a smallest eigenvalue simply the nth power of the smallest eigenvalue of P by spectral theory. And so, yeah, so it turns out we can apply this to the Harrow et al. Example. We just these two channels satisfy the conditions, and by choosing particular numbers, we can find that this C Chernoff coefficient with parallel strategies is bounded by some number 14. Actually, in the paper it's slightly smaller, but the point is it's not infinite, which is the adaptive Chernoff coefficient. Why is the adaptive one infinite? Because for two channel uses, we already obtain alpha equal beta equals 0. And so that means the log is infinite. Yeah. And so from some other paper by colleagues from Warsaw, I think, Krawiec, Pawela, and Kuchała, they even found QC channels. So these are two channels that are implementing measurements and then preparing a basis state. They can also be engineered in such a way that the Duan et al. Criterion applies. We can get a lower bound on the smallest eigenvalue, and we get an upper bound on the Chernoff coefficient. And so these kind of constructions, they all rely actually abstractly on a result by another result by Duan et al. That characterizes precisely when this adaptive Chernoff coefficient is infinite, namely, it is infinite if and only if there is an n in an adaptive strategy of n channel uses such that alpha equal beta equals 0, exactly. So there is some finite n so that the channels become perfectly distinguishable. And this in turn can be characterized in terms of linear algebraic properties of the Krauss operators of the two channels. This is all from 10 years ago, roughly. And so, yeah, that brings me to the conclusions. That's kind of the last slide. And probably, I mean, maybe I'm going to be cut off by my battery dying. So finally, we find some kind of quantitative separation for adaptiveness versus non-adaptiveness. And it's in this Chernoff. And in fact, I didn't show it, but in the paper, we also extend it to the Hoeffding settings. And the advantage requires, in some sense, genuine quantum channels, but in the sense that classical quantum channels is not enough, but for example, quantum classical channels, yes. Or in fact, the Harrow et al. Example is an entanglement-breaking channel. It's also a measurement. It also measures, but not like I mean, measures the input state and prepares some output state. But there's some non-orthogonality. So like, it's enough to have a little bit of non-orthogonality, and that's enough quantumness to provide an advantage. And so, yeah, one of open questions that bugs me since we wrote this paper is we know that mathematically these adaptive strategies are not the most general thing. There is kind of yet another kind of tensor that you can use to process n channel uses to discriminate them. They are these so-called non-causal processes. And as far as I know, we don't know under which circumstances non-causal processes can distinguish two channels perfectly. We don't have separations between the non-causal and the adaptiveness and so on. That is something that I'm thinking about sometimes recently. But I should also say that these non-causal strategies, they are mathematically well defined, but I think the consensus is that they're not physical. I mean, it's hard to justify those as physically meaningful. Okay, thank you very much. Okay, so that's the end of the talk. The questions I'm happy to answer. Maybe go out of the full screen mode.
So I would ask the participants if you have any questions. The floor is open for questions. Please unmute yourselves and ask the questions.
Yeah. Could you please say about channel capacity, whether they belong to sub-additive, super-additive, additive, or adaptive and non-adaptive channels? Professor Winter. Hello, Professor Winter.
Sir, I think there is a bit of lag. There is some network issue. We are not able to see him.
Yeah. So then we can close this session.
If there are no questions, yeah, we can close it.
Yeah. So thanks all the speakers in this session, and I announce closing of this session. Thank all the participants.
Thank you, Professor Guru Prasad, for chairing the session. So this is an announcement from the QIQT organizing committee. Like there will be tomorrow morning session and evening session. The tomorrow session will start from 10 a.m. and it will follow. So we'll inform you in the due time. So thank you all, and please tune in